So hi everyone. Today we will try to understand what are conditional GANs, aka called as CGANs. So by the time we are making this video, so we have covered topics like generative AI basics, variational autoencoders or VAEs, vanilla GANs, cycle GANs, pixel CNNs. So now the next in the generative AI modeling part is what are conditional GANs and why they are used. So first of all, let's understand what is the requirement of CGANs and like what actually they are different from the vanilla GAN. So if you have ever tried out GANs or like seen my previous video, so in most of the generative models we have trained, be it vanilla GANs, be it autoencoder, variational autoencoders, be it 6 pixel CNN, the major point of issue is key you are training that particular model on a particular data set, and now eventually it's dependent upon the generative model that it generates some random sample out of it. So for example, if I one day wish to train MNSIT dataset on using vanilla GANs. Now, what I wish to do is I wish to generate a image for a particular class, say 7. So for digit 7, I wish to generate images for that. So in case of vanilla GANs or variational autoencoders, this is just not possible. Like you really can't provide a condition. So in that case, what you need to do is you would be generating multiple samples and eventually will wait till an image for digit 7 is generated. Now, for example, now this is a case where we have just 10 classes, MNS dataset. Now, assume that when you're training your model on some phase datasets, eventually the end goal of the problem is you wish to generate faces with certain specifications like red nose, big eyes, fat cheeks, etc. You wish to provide these attributes also. But in case of vanilla GANs or variational autoencoders or pixels, and like most of the models that we've discussed earlier, this is just not possible. And this is why CGANs came into the picture. So CGANs are the ones that we are looking for and can really help us in unlocking the power of generative AI. So what does they do? You provide some different attributes depending upon the data set, and eventually they would be able to generate an image depending on those attributes. Now this is actually a use case that we can implement now. So if you are training a conditional GAN on some on MNS dataset, so in the end of the day you can expect like you provided an input, I wish to generate images for digit 2, and eventually it will able to generate it, which vanilla GANs or variational autoencoders or like other basic CNNs won't be able to basic GAN structures won't be able to do. So now, as we know why conditional GANs are used and why they are important, I think let's go and understand how they work and how they're different from vanilla GANs. So in vanilla GANs, we have like just to summarize a bit, or like if you wish to know in detail, you can go and watch my previous video. So in vanilla GANs, we have a pair of generator and discriminator, where the generator tries to generate fake images and the using random noise, and the discriminator tries to classify whether the image generated by the generator is fake or real. I think this is what in the whole vanilla GAN is all about. And the system is adversarial, that they're trying, like the generator is trying to maximize the classification error while the discriminator is trying to lower that classification error. I think as simple as that. Now in conditional GAN, we are making a couple of changes. Let's see what are they. First is the generator intakes random noise similar to vanilla GANs, but alongside that it also intakes labels for which image has to be generated. For example, if you are working on MNIST dataset, alongside the random noise, you would be also providing the class name. Okay, random noise plus class 2 or random noise plus class 4, something like this. And also the discriminator won't be just checking for whether the image is real or fake, but also for to which class it belongs. So you're getting my point. So if it can be the case that generator generates a digit an image for digit 3 that looks very real, but the label assigned to it is 2, so in that case also it would be called a fake. So now discriminator has two jobs. One is to detect whether the image is real or fake, and also to match it with the class it belongs to given the label. So the generator will pass it the generated image as well as the class key. Okay, this is the image that I've generated, and this is the class to which this image belongs to. Now the discriminator roles. Now the discriminator has to classify this image on two bases, and even of the if one of the criteria fails, then the image is taken as a fake. So even if the image is looking real but the label is wrong, or vice versa, in that case also the discriminator has to classify the image as fake. So, but still you need to remember that this is still a binary classification problem, not a multi-classification problem. So the class label has nothing to do in the end goal. When we will be training, when we would be having the error, when we're training the model for optimizing over the error, it still remains a binary classification, that is fake or real. Now the definition of fake and real has changed a bit. So for fake, we are now having two criteria. That's the only issue, else everything looks fine. So apart from this meta information that is getting provided with the random noise, nothing changes. It remains the same as similar to vanilla GANs, where the generator and discriminator are fighting with each other to optimize over the binary cross entropy loss. So discriminator will try to reduce that cross entropy loss, while the generator will try to increase that cross entropy loss, calling it an adversarial system. I think all these basics of GANs I have already covered in a previous video, so I won't be covering that. Now big question remains that how would be able to attach label information with an image sample. Now image would be a two cross like n cross n and numpy array, while a label is would be a category or integer. So how to attach these information? So it is a classic case of multimodal modeling. So in my previous video I have already explained what is a multimodal modeling while explaining about dolly, so you can watch that. So in multimodal modeling, the basic idea is ki, the model is trying to incorporate multiple data types within the same problem statement. So here you can see it is a very classic case because we have image dataset as well as label information. So how are we going to do how are we going to merge these two information together? So what we would be doing is we would be generating an embedding for the label category. So in case of MNIST, there are 10 categories, so we will be having 10 embeddings. Now we would be expanding this embedding equal to an n cross n 1D array. Now where n cross n equals to the dimension of the image data set, right? So for example, if we have MNIST data set which is 28 cross 28, assume that the initial embedding that we generated for label category is 10. The size of the embedding is 10 for each label. Now we will be using this 10 to expand it into 28 into 28 dimension. Makes sense? That is 784. So now this embedding would be expanded as a 784 flat array. Now we would be reshaping this flat array into a 2D image. 784 would get reshaped as 28 into 28 into 1, and then eventually this particular 2D image would get integrated with this image, the actual data set that we have, the actual dataset image that we have as one of the channels of the image. Makes sense? So if we start again, so initially we have an image as well as the label of the image. So now using that label, we generated an embedding. We expanded that embedding into equals to 784, for example. If the dimension of the image dataset is 28 into 28, now using the 784 flat array, we would be reshaping that into 28 into 28 2D image, and then we would be integrating this 2D image into the actual image. So in short, the label information is automatically integrated within the image itself, and that is why the whole problem remains a binary classification problem only, and it doesn't go into multi classification. I think the idea is very simple. Now look at the training flow. So first of all, we will taking a multi-class image dataset. Even if you wish to take a binary classification dataset, not an issue. This would be called as our real images. Now we would be generating fake dataset using random noise and random labels, which would be an input for the generator. Now using this random noise and random label, the generator would be producing fake images depending upon the random label associated with the image. Now we would be mixing the real and fake datasets. Real is the actual dataset, fake is the one generated by the generator, and we will be feeding this mixed dataset to discriminator to classify between real and fake. Once the training is done, the discriminator would be discarded and the generator would be used for generating images for specific classes.